This is Mr. Champlin, and we are going to solve a couple of these SAC problems. SAC Chapter 2, number 5. So we're going to start with number 5 here. And the problem reads that depicted at right is a metal ball of mass m, negligible diameter. A ball is suspended from a fixed support by a massless string. The string is just barely in contact with the cylinder of radius r that is fixed in position, so that it can neither move nor turn. A person pulls the ball up and away from the cylinder until the string is horizontal. The person releases the ball from rest. It swings down and then around the cylinder as the string wraps itself around the cylinder. How fast is the ball going when it is at the highest position it reaches, subsequent to the string starting to wrap itself around the cylinder? So I'm going to start at the initial situation. So initially, this string and mass are pulled up this way. So it's going to look like initially we have this mass and it's going horizontal with the mass attached, and that has a length of L. And then later, final condition, so the string comes down, swings around, wraps around the cylinder, and then continue to wrap it. But the highest point will be at this point before it starts rotating again, and it's attached here. So it's still moving as it's going around this cylinder. So we're going to go ahead and use conservation of energy. Mechanical energy initial equals mechanical energy final. At the highest position, it is at rest and it's released, so it's all potential. So we'll call that gravitational energy. And then when it swings around the cylinder and wraps around, it's still above the lowest position, so it has potential, but it also has kinetic because it's moving. All right. We know the formula for potential energy is mg y initial, and final potential is mg y final plus mv squared. So it looks straightforward. The really only difficult spot is those heights. The lowest spot is let's see, I'm sorry, the initial spot, because it's all the way up horizontally. I think it says that in the problem. It's L above the lowest position. So this initial yi is L. YF is a little tricky. Let's see. So when it wraps around here, we're going to need the height between here and here, which that's not a problem because we can just take the difference between L and H. But then we need this additional height where it wraps those up. So let's see. Y final, I'll write that all over here. So we'll say this distance is y1, and this distance that wraps around is y2. So the y final is going to be the sum of those two, y1 plus y2. y1 is easy. y1 is L minus h. So let's write down L minus h. That's y1. y2, not so easy. Well, what I'm going to do is, we know L total, this whole length is all the strings, so L total equals this length of, it's part of it, h, plus the amount that wraps around. Well, since it's vertical, as you know, this is vertical, the highest position. It goes halfway around a circle. A full circle is 2 pi r. Halfway around a circle is 1/2 2 pi r, which would be plus pi r. And then the remaining distance, y2, will be added on. All right, so then we can, oh, I forgot the r here. Okay, so y2 equals L minus H minus pi r. Do they give us r? Let's see. They give us, supposedly, a cylinder radius r right there. So that's the radius. We know that. So I think we can substitute all of this in. All right. First of all, masses are part of all terms, so masses will cancel, and then we can go G yi B L. That's the length of the string equals G YF, which is the sum of these, so that's going to be L minus H plus Y2, which is this term, plus L minus H minus pi R. And then plus the 1/2 V squared. Alright, so we got a lot of terms here. So let's see, we're going to have to combine all these terms. So it's going to be G, L. We're going to combine everything in these parentheses. So we got two L's, so I'll write down 2L minus 2H minus pi R plus 1/2 V squared. And then we're going to, I'm going to clear out this 1/2, so I'll multiply through by 2. So it'll be 2GL, and this will be 2G, 2L minus 2H minus pi R plus V squared. Almost done here, let's see. So then I'm going to just subtract all that out. So 2GL minus, I guess I can multiply this through, so this is 4GL. Oh, strange math here. And this is going to, since this is subtracted, you're going to add the other side, so it's going to be plus 2H. Oops, that's going to be 4. So it's going to be 4GH plus 2G pi R equals V squared. Combining all these terms, we have 4GH plus 2G pi R minus 2GL. Make this correct. Equals V. And that's it. All right. All right, the second problem, number 6, uniform block of mass M, where's mass M, has the shape of a cube of edge length B. edge length B right there. Let me write that in there. B. A flat, straight, horizontal board of length L, width W. So length L, width W. Has two lines marked on its face. There's line 1, there's line 2. Each line extends across the width of the board and is perpendicular to the length of the board, and that's how I showed it there. Lines of distance D apart, there's D, from each other. The top face of the board is so slippery that we can consider it to be frictionless. A person lifts and props up one end of the board high enough so that the board makes an angle theta, right there. This is angle theta, with the horizontal, while the two drawn lines are still horizontal. The board is fixed in place in this orientation, then the person brings one side of the block into contact. Right, there's a contact. Then with the top face of the board and positions the block so that the lowest edge of the block is aligned with the higher drawn line of the board. The person releases the blocks from rest so skillfully that the block slides down the incline without spinning, so it doesn't rotate. How fast is the block moving when this lowest edge of the block is aligned? Alright, I'm going to add one more diagram to kind of relate this D length with this angle. If you just make a smaller right triangle from there, I'll draw that here. So this is theta. This is D. And we'll call this Y, the height, the difference of the height. Alright, so this is a pretty straightforward conservation energy. I'm going to get rid of all these marks over here. Okay, so mechanical energy conservation, MEI, MEF. So it's going to have, it's released from here, so it's at rest. So this is UGI. And this is, it's really not any potential at the bottom. That's the lowest. We're going to call this the reference point. So this is the reference, so this is 0. So this will have no gravitational potential, only kinetic. So it'll just be KE final. So it's going to be MGY sub I. And this is 1/2 MV squared. Down here a little bit. If you look at this triangle, right triangle, which is taking the side view of this incline, we could say that the sine of theta is y divided by d. So therefore y, the height is d sine theta. So I'm going to substitute that in for y here. Mg d sine theta equals 1/2 mv squared. Both sides have mass, cancel those. Multiply both sides by 2. There you go.